So let's get started. I guess first thing I would like to say is again to remind you that the assignment 2 has been released, and it will be after the Halloween. I mean, probably you should take the time to do the work, and then just make sure that you know what's going on. And I hope you would spend some time and work on those. I can see that if you try to ask the ChatGPT, they may give the answer. But at least you should try to work it out, or if you try to seek help, then make sure and understand what's going on, because that you expect to answer the same question or similar question in the exam, right? Because assignment is going to cover the things that I think is important, right? Exam again is asking something important as well, right? So so it's going to be more than 2 weeks time. So I hope you should be able to finish them all. Shouldn't be a big issue here. And the next thing is the self-quiz is already there. You can go there and check it out. There's no credit. You can do it whenever you feel happy. You can just try to see how well you're doing, and then that's checking. Maybe good before you do assignment or after you do assignment is fine. It's not credit bearing. So today, the goal of today is to, I guess we can cover half of it. Okay, we'll go over the starting point of talking about data, right? So far we have is more or less there's no data there, right? And not yet. Except the first chapter, we are summarizing the data, right? We didn't actually generate new knowledge, but we just talking about what we have, right? What the mean, variance, kurtosis, skewness, correlation, talking about what the data already inside the data, right? You just brush off the dust from the thing you discover under the ground, right? Not really trying to discover general new knowledge. Okay. And from today's class to the end of semester, what we're going to do is we try to generate new knowledge or prediction or something that can extend what we know from data, right, to the general idea. Okay, so this, maybe I go to the slide, make it more clear what we're doing. But this is the underlying, right? Basically, what we talk about is when we talk about distribution, right? We talked about last class. So now we talk about data. Suppose we have data, right? And then the data, what we got is not generated from the nature, right? Or depend on who you talk to, right? Then it's a random experiment, right? Because if you talk to every one of them, then there's no problem. But the problem is that you're never able to talk to every one of them, right? Or the future, you want to predict or you understand, is something that related to the past, right? You consider the future and the past are something similar, right? Otherwise, if there's no connection, then it's not something we can say. Usually, we would use the term called population, right? Is the things that we want to know. All right, then probably you can imagine that it's sometimes you look at advanced topic that we call data generating process, right? How to observe data generated by population, right? It's like what is underlying thing we want to know. Say like the age of income in a given city, right? Or how much they want to pay for it, how much they want to buy for it, or the stock price tomorrow, right? Which is subject to, I don't know what the number generates, right? It's affected many things that it's not controlled, right? And we are usually able to observe the whole population. Okay. And what we observe is a sample, right? So the big picture is there, but we are unable to look at every single individual in the big picture. We just handpick some of the sensitive, hopefully representative thing from the population, from big picture, and hopefully the conclusion we drawn or the data we learn or the knowledge we generated from the sample, which is the data we have, is going to be a good guess from what's happening in the population. Right? For example, if a new product, you want to see how much people would pay for the product, right? So usually if you're marketing, you just try to do a small scale test, right? Maybe go to a city or go to even a street somewhere and try to ask or try to test how people want to pay for that, how people like it, right? And then you're not going to do a full scale test, right? You're doing small scale and see how much people want to pay for that. And if that works out, and then you will try to extend to the whole country, right? So that is the idea. Or we want to know, say, how much people are making, right? Then what you're going to do is just try to, each city you try to select some people to ask and then do a survey, right? And hopefully the people you interview, you talk to, is going to be useful, right? To guess what's going on for every people in the city, in the society, or in the economy that you hope to work on, right? So basically, is the data we get is a small part of thing you want to study, right? You want to say this small part going to hold for the big part. So that is the ultimate goal. Okay. So maybe I would like to draw your attention on this technical slide. I mean, this is something that I think is useful. So you can imagine that we are concerned ourselves with, say, some measurement or some numbers of the population, right? And you can easily summarize if you have access to this, but you never. But your access to this is the it's called the frequency table, right? You look at the bar chart, right? Say how many people make so much money, right? And this is something you might know, right? And in this table, you can summarize the F by, say, the mu and the variance, okay? And of course, we want to note F, but that is too ambitious, right? Because remember, the fact is you only have some part of the data. If you use this to guess the F, almost not possible, right? So let's focus on some less ambitious goal. Is instead of guess what is the F, we guess the number we care. That usually we care for our decision is the mu and variance, right? Look at the mean, population, and the variance, right? If you put in the stock market, right, you may tempted to think I want to predict the stock price for every minute or today or next week. That will be too ambitious, right? But it'll be okay if you predict the mean price or the mean return or the variance of return with the risk. That may be a manageable goal, right? Looking at the past price history, it's okay to predict where the price on average will go and how fluctuate they are. That is possible to do. But if you say I try to predict the stock price in the morning will follow a certain shape and how it go up and go down, that I guess that is, I mean, unless, I mean, they have a crystal ball, I don't think that it's possible to do it. So, and when I was a student, I was like, okay, why we focus on this too? Because now I understand, because you're looking at a small part of the what you can observe, then try to guess this F is almost like you can do it, but that would be very difficult, right? Unless you know some physics, right? That may be followed by binomial. There's something or radioactive follow exponential. You know the rule, then probably it's okay. But in general, you don't know that, right? Then the easiest way to estimate the mu and sigma square, right? But if you make a further assumption, you can do an F, right? Because if you know it follows certain type of distribution, then probably can guess, right? Because suppose you know this follow Poisson, right? Once you estimate the mean, then you know or variance, right? Then you know everything, right? Or it's binomial, then you can, once you have mean and variance, you can pretty much know what the F is, have a good guess. But if you don't make assumption, that is the best you can do is to estimate this too, right? And sample is basically pick up some element from the observation, from the population, right? So you can imagine that, say, the stock price idea, right? You can imagine that actually there are a parallel universe, right? What we have is one of the universe, right? So that is the thing that you think in the stock price, right? Because there's nothing to pick from the stock price. But you can imagine the future can be, there are multiple universes. In the future, we go to one of them, right? There's one we pick, okay? And the random sample means we have a random draw from the population, okay? And one important thing that is the random sample would offer is that when you try to close your eye and draw a data observation individual from the population, what you actually draw will be same as F. Unknown, but this is the F is the thing. That is the helping us, right? Because say suppose F following this particular shape, right? How likely you draw a particular shape depends on how frequently it's in data, right? So that is very important, okay? And if the sample is not random, then you lose all the nice properties, right? Because if that is not true, right? So the data you got is not, cannot tell anything about the big thing, right? So usually the notation we will use because they are random sample, right? And these are all random variable. So I use capital letter X, right? If you notice the way I write in the slides is, or same as other textbook is, for random variable, I will use capital letter. For number that is a constant, is not random, I use a small letter. So this or I have n observations, that will be x1 up to xn. Okay, I would use this notation. So in this class, and same as all stat class, all intro-stat class, we focus on what we call simple random sample. Okay, and what does that mean is you will imagine that you are able to have a technology that allows you to access to every individuals in the population you're interested, and also each individual will pick up with the same probability. Okay, that is possible in our technology, but do note that that's not that easy. For example, in say the easiest thing is think about election. Okay, in US now, I think it's a hot thing now. It's like the Democrat and the Republican and also other small party anyway. But you would notice that when you randomly ask a person, right, then it is possible that you pick up maybe equally likely that half of them may be Democrat, half of them are Republican, but they may not be representative, right? Because historically, there are more Democrat. I mean, of course, now currently might now have more Republican, but so this, I mean, with the shift and back and forth. So when you get a data, you randomly draw 1,000 people, right? You will figure out 500 are Democrat, 500 are Republican. Then you have to adjust the data such that to try to rescale the data, make this data is useful, okay? But we in this class we will focus on the case where we have technology able us to draw that idea, right? Have able to control, make sure everyone is equally selected, okay? And that's not that easy because suppose you use a telephone survey, right? Then if people don't have telephone, then they will never got survey, right? If you use internet survey, then if the one who don't go to internet, that's a problem, right? So that is not that easy. I mean, there are many ways to make sure that this would happen at the end, but it's not my goal to do it, okay? But that's the same as I always said, right? So the simple random sample, the most important part is this independent, means that covariance is 0, right? They all the same mean and variance, which will be the next slide. And of course, the second consequence is every random variable will follow the P or the F, that is followed from the population, okay? And that is very key part that would generate the nice property that we want, right? Otherwise, if this is not true, it follows something different from the population we study, then the sample we got doesn't carry the information from the population, right? Then there's no hope to do anything, okay? So that is the main property that we will use, and then I think, as I understand it, 90% of the stat that you learn in undergrad is basically makes this assumption. It's called the simple random sample. Okay. Saying that if we got the observation and observation, right? Because you draw it independently, okay? And for the population and the independent, and that means that the expectation of every random variable has the same mean as the population one, okay? And the variance will be the same, and the covariance of any of them will be 0, okay? So that is the very key part that drive our proofs, although we don't do any proof, but I want to let you know this assumption because that is the key that drive all the result behind. Okay, and I will try to explain what is the implication there. Okay, probably I can skip this part. Okay, so now quite an irony that we're halfway in the semester. Now we define what is statistics, right? Because you would be wondering, I mean, what we're doing for the first half of the semester. And statistics, contrary to what you believe, okay, it's not a number, it's a function. So just like random variable is not variable, right? Random variable is a function as well, right? It's a function that map outcome to a number. It's called random variable. So statistics are not a number. It's also a function which transform the sample to a number again. Okay, to remind you that it's not a number, it's a function. Okay, it's a way that how the data you observe map to some number. Okay, and function, right, is a fancy name, but you can imagine it's a method. Okay, it's a method. You convert your data to some number. Okay, and you can imagine that that is like a summary of what the data is, right? Or reduce the dimension of the data reduction, right? And actually, you were surprised. Actually, we have seen that all the time because sample mean and sample variance is a statistics, right? Because you collect the data, you calculate the mean, right? You just reduce mean is like the way that you summarize your data into a number. Sample variance is the way you summarize the dispersion, how spread data into a number. Okay, that is called statistics. Okay. And we know this is the one, right? The sample mean. Now do note that because each sample is a random variable, okay? Statistic is also a random variable, right? So that's why I will always use sample mean. You notice the slide, the notation, as capital letter, as opposed to the small letter in the first chapter. Why? Because everything we have is a random variable. Okay, so that's why you have to learn random variable before we come to this chapter, right? Because otherwise there's no point. That's right. And it's very simple, right? Just add all the observation over the n. Do note that because based on the sample you got, which is a random event, right? So it means that this sample mean is a random variable, right? Depends on the sample. Maybe you can keep your voice a little bit lower. I mean, sorry. Yeah. So itself a random variable. That means that you have distribution, right? And do remind yourself that each x would follow the population f, right? And x bar will follow that, which we will prove soon. But let's say something, okay? So you see this, right, will be drawn from some f, okay? And the question is xi, okay? The question is this x bar, what type of distribution you will got, okay? In general, we don't know. In general, no idea, okay? Because as I said, right, adding distribution even though identical, need not be the same. Okay. The only thing you can know is normal and abnormal is normal, but you add two binomial, it's not binomial. Okay. So the question is, what is X bar looks like? Okay. In general, I don't know. We have no idea, but that's what we call the central limit theorem, which we'll talk about later. This, is there any hope to know anything about that? Is when n is super big, okay, turn out that this is the bell shape. Okay, this is called central limit theorem. Okay, and we know that these have mean mu. Okay, and central limit theorem tell us that it will be centered at the mu. Okay, and also later you also say the law of large number also said this is exactly when you get more and more n. Okay, this one will collapse like this. The bell will eventually like this. So if you increase n more and more, that collapse, that you exactly get what we want. So that is called law of large number. Okay, the two things that ensure that if you have infinite amount of money, you do enough sampling, eventually we discover the truth. Okay, I mean as close as we want. Okay, but anyway, that will be something we talk about soon. Okay, because why we care about this guy? This guy is, I want to know mu at the end, right? This X bar, which we'll talk about next class, is called estimation. X bar is the way as an estimator to estimate the mu, right? Is to guess what the mu is, because as I said, the goal of our at the end of this is to estimate mu or estimate sigma squared, right? And this is the goal, and X bar is the way that to go forward, right? So we'll talk about this quickly, but don't worry, you'll be soon there. Is that okay? I just go to the next slide. Okay. But don't worry, this is a thing that I go ahead a little bit myself. Okay. So as I said, X bar is a way to guess. Okay. And the first thing is, turn out the first nice property is first is called expectation of this. Okay. And we'll talk about next class. Sorry, next topic is called unbiasedness, which means that if I have one sample, I have one sample mean. I collect another sample mean. I have other sample mean, right? I have many sample mean. Okay. Suppose I do this. Of course, you only do one in the real world, but suppose you can do this multiple times. Okay. Average of this multiple times, average of all the sample mean is exactly mu. Okay. That is what we will talk about in the next topic. It's called unbiasedness, right? So that's very important property of this one is on average we're getting right. Although we just do one, but there's some confidence that if we can repeat that it's going to be there. Why it's important? Imagine you do experiment in the lab, right? In one lab they do this, the other lab they do that, the other lab do that. In aggregating all the outcome of all the labs, we discover the real truth, right? So that is the basis of scientific discovery. Right? And second one, we have the variance of that, right? And we will show you that when n go to infinity, big enough, this variance go to 0. Okay. And what about P and F? Okay, that's what we said. We would talk about law of large number, and we'll talk about the central limit theorem. And possibly you will say these two rules is the fundamental for our course. And also, if you study advanced statistics, you will study different version of this. Okay. And basically the all the research, I mean not all, but majority of research these days are basically trying to establish different way that central limit theorem would hold. and law large number would hold. Under more advanced setup, okay, if they don't hold, what it will look like, right? Because if when we have large sample, very large sample, E should have nice property. If not, then things fall apart, right? And the very last thing we talk about in this topic is we go back to the idea that we will talk about the student T distribution, okay, which we will be going to there. And then the last case is we focus on binary data, okay? And so far we have is X is any number, look at the stock price, right? And if you look at binary data, it's yes or no question, right? So suppose you ask people whether you support Trump or Camara, right? And that is, well, you Harris, right? In one way or the other, right? So binary, right? Or you are male or female, or you like this class or not, right? Binary, okay? It's binomial idea. So you will see there's some very special thing goes on here. Okay. So now we try to argue the following, which is we call unbiasedness, which we'll talk about. We define it in next class. But at least what we said is, suppose we have many sample, right? And each sample, we can calculate sample mean, right? Average of this sample mean that would be same as the population mean, okay? So that is the main result, okay? So do look at this part, it's just definition, okay? This is definition. There is no knowledge. The knowledge part come from here, okay? The red one is the thing we actually should prove, but we didn't have time to prove, but you can easily prove that. I mean, look at the gray box. It will be can be proven that that is if we do it many times, right? And there's a hope that we discover the truth. Okay, then we have the confidence in the process that's going to right. Okay, on average is correct, right? Unbiasedness. Actually, look at a tweet by Elon Musk. Actually, he said the same. I mean, he said he was being criticized for being too optimistic about his prediction about the future or how fast he delivered what he predicts, right? And he said, I mean, actually half of his prediction is right and half is wrong, but people focus on the wrong part. But he said on average he's doing correct, right? Look at rocket, maybe it's faster, but on car he's slower, right? But on average, I think he's in terms of tech prediction, he's right. But that means unbiasedness, right? Means on average, it's right. Means that sometimes that is fast in terms of Elon Musk's idea, right? Sometimes it's faster, sometimes slower, right? So stock price, your prediction, right? On F, 50% that you predict this, 50% is higher, 50% lower, right? So that is called unbiasedness. Okay. And the proof is actually not very complicated, but we're not going to do it. But that is, we'll do it by example to convince you this is right. Okay. But I'm not going to do the proof, but the proof is very similar. So the idea is like this, right? For population, something we study, right? We will do M sample, but do remind yourself in a real world, we just do one of them. Okay. Which one? Depends on nature. You don't know which one you do it at the real world, right? Because you close your eye, pick up some people, right? And the nature will decide which one we pick, okay? But suppose we're able to every single of them, right? And average of those divided by M actually is mu. So that is the content, okay? So let's look at this example. Okay, I think this would convince you what we're doing, what I'm saying, because otherwise you never understand. So I like this example because in the population you have three numbers: number 1, number 2, and number 3. And maybe you can keep the voice down a little bit. Yeah. So if you randomly draw a number, right? That's a random sample. But if you know this is the three-numbered population, you will know the population mean, right? There's no probability there, right? Just add up three numbers divided by 3. The mean is 2, right? So, but of course, in the real world, we don't have this. But suppose this is the case too, right? We know it. But do you note that we never know the population? Okay, we never know how many of them, but suppose it's the case. Okay. And suppose you just close your eye and draw one number there. Okay. What will you got? Because close your eye, so each number will realize with probably 1/3, right? That is what you got, right? Because sample mean is same as, because only one, you only draw one guy. Sample mean is exactly observation. So sample mean is either 1, 2, and 3, okay? With equally likely, okay? So the first question would be, what is the expectation of the sample mean, right? So on average, what you got? So 1/3 of the time you get 1, 1/3 of the time you got 2, 1/3 of the time you got 3. So average of this is actually 2. So that means that the average of the sample mean, or the expectation, is exactly the same as 2. So that means that if you're able to do this many, many times, you discover the truth. Okay, so that's the reason behind why a lot of now the election, I mean, there's someone who tried to collect all the pool together to average, especially the real clear politics, right? They combine different pools and try to discover the truth, because average of this, if each one is random sample, then should able to get you the ground truth over there. Also, this is the idea. Yeah. Of course, you may say, okay, this is rather easy because I focus on sample of size 1, right? Why don't I make it more fun, focus on sample of size 2? So I close my eye, I draw sample there, okay? And because each is independent, right? So that means that I draw it, I put it back, right? So because each draw should be independent. That's called sample random sample, right? I draw a number, I put it back and draw it again. It's okay, I draw the same, but I don't know if it's the same or not. Okay, I don't actually know whether the next draw is same as before, right? So basically, I draw a guy and record the number. I erase my memory, I do it again. Okay. So in that case, what you would do is you have two numbers, x1, x2. 3 numbers are possible. Okay. And these are the sample mean in the first table there, right? 1 and 1, the mean is 1. 1 and 2, the mean 1.5. 1 and 3 is 2. So this number, in case you are not understand what's going on, this is average of these two numbers, right? And this is 1.5 is 1 and 2 is 1.5, the average, right? 1 and 3 is 2. So these are all 9 combinations. It's possible for you to draw each sample. And if you happen to be, say, 2, 2, the sample means 2, right? So remember, each 9 outcome is equally likely, right? Because 1/3 for each, right? So it's 1 over 9, okay? And you count how many of them is 1 of 9. How many of them you get 1.5? The 2 out of 9, right? How many if 2 is 3 out of 9? 2.5 is 2 over 9, and 3 is 1 over 9, right? Just kind of number, because each outcome is 1 over 9, right? So what's the expectation of this sample mean, right? Because this is the distribution, right? This is called sampling distribution, right? Well, we have this guy. And we have, just remember how we do it. Multiply vertically and add horizontally, right? First multiply vertically and add horizontally. That's what we get, 2. Exactly the 2 we have. Okay. Of course, I don't want to say sample size is 3. Sample size 3 is we say, okay. You can do the same logic, okay. But you can easily check that if you do more, that the same idea goes on. Okay. Of course, there's a proof behind, which I will skip. Actually, the proof is rather simple. But if you do 3, that was something like this. I'm not going to do it, but you can try to work it out if you want to have fun. But I guess we are all very busy, so just trust me, you get 2. Okay, if you want to do it, you're welcome to have fun, but I guess we are all too busy to do this. Okay, anyway, so there's a proof. The proof is not very difficult, just 5 single steps, but I don't want to bother with proof. Okay. So I hope I convince you that if you do many sample hypothetically, and each sample we calculate sample mean, and average of all these four possible sample mean will get us the ground truth. Okay, and that is the reason why sample mean is good, right? Because we get the ground truth. Now the next question we want to know is, we do have the sample mean on average is mu, right? The next question is how accurate it is, right? Because the very natural question, right? We know on average get there, but is it going to big variance, small variance? Okay, and turn out that, okay, we can have formula. Okay, again, the left hand side is definition, right? Do remind you that this is definition. Okay, and this is the result. Turn out to be, we can prove the variance sample mean, okay, it's 1/n of the original variance of the population. Okay, which is surprising, because of you calculate the average, right? So the spread will be less, right? Because suppose you have a very spread out distribution, right? You get a very extreme value, but you're also able to get an extreme value as well. So averaging those out, on average, the variation is less, right? You average things out and the variation is less, okay? And turn out that is a very nice formula there. You can easily prove that. It's not complicated proof, but I don't want to further use that. But do note that this formula will be very important. We will do all the result based on this. A lot of the result will based on this guy. Okay. So what does that mean? I should draw a graph to convince you what we have said, right? So I have population there. I don't know, this underlying is F, right? Or the P, whatever you like, continuous is F, right? So suppose this mean is like here, its variance like here, okay? What we know is, maybe it's other color, right? What does sample mean there? I don't know what it looks like. Can be any shape, right? Because it depends on the sample size n, okay? But I know that the average is still mu, okay? And the variance is actually less. Okay? If you have, say suppose the case is like, suppose x bar 3 here can be something like this, okay? For example, okay? And then you will see that if you have, then can be x bar 4 getting smaller. Okay, I don't know the shape. It can be anything, can be very crazy shape, but at least I know the variance is shrinking. Okay, at the end, when n go to infinity, right? What I know is when n go to infinity, right? Because until infinity or close to infinity, that will be something like this always. Why? Because the variance is 0, right? So it must be concentrated in the middle, right? Because I know that on average is mu, so it can't be go anywhere else. Where it must be centered there. Okay, so that is the idea. Okay, so that is the what we are doing there. I hope that makes sense to you. Okay, do you know that this is very important? It's divided by n. Okay. Why this is important metrics? Because later you will see that is something we call standard error. Okay. Standard error of the mean. Okay. Even you can see denoted by SE in many textbooks. It's actually a standard deviation of the sample mean. Okay, and sometimes we call standard error of the mean. Okay, we're being lazy, but that is taking square root. Okay, well, we've seen this sigma over root n many times. Okay, don't worry, this is something that will be there all the time. Okay, so this is the part that you will be seeing this a lot of time. Okay, now I guess it would be not easy with notation, so let's go to example to convince you that this is not something to take. After this, I'll break. Okay, so don't worry. So three numbers 1, 2, and 3. Okay, again the sample means 2. Then if you all know this number, what is sample population variance? To know the population divided by n, not n minus 1. Okay, so you take every number minus the mean square, add them all up, actually turn out to be 2/3, right? Because it's 1 plus 0 plus 1 is 2, 2 over 3. Okay, now the next question is I suppose I do the sample size of 1. Okay, so we have been known that the expectation x bar is 2, which is same as the mu, right? And we have only 3 possible choices, 1, 2, and 3. Okay, and they are same probability. We want to calculate the variance, which is this guy, right? So it's 1 minus 2 square is 1 square, right? 2 minus 2 square, 0 square. 3 minus 2 square is 1. Okay, so what's the variance? Is this, that is the vertical multiplication, horizontal addition, right? That's the rule, right? So 1 times 1/3 plus 0 times 1/3, so it's 2/3. All right, so you can see that the same, because this is n is 1, the sample size is 1. Right, so if you do the sample size 2, okay, the same logic, okay, you notice that that will be the variance smaller, right? Because actually more concentrated at 2. Okay, you can do the math. Okay, how to be 2/3 over 2. So it will be population variance over 2. Okay, so that means that the larger the sample size you got, okay, that is a good news because the variance gets smaller, right? The bigger the sample size, you have more confidence that your sample mean you collect will be more accurate, right? Because the variance is smaller, right? The more you get, actually you get a so large, very large that actually you believe that what you get is actually what it is, right? So I will not continue, but you can see you go free the same. Okay, maybe I just put it here and then we have a break. I know there's a lot of things to absorb because we're not going to do any proof, so there's a bunch of facts that I lay out, and we will actually apply it in the later, because I think this topic is more like later foundations. So probably you may not see the importance here, but at least what we're trying to do is trying to tell you that when you draw a sample, it's a random variable, and this is a property, and we'll use it for the next topic. So it's like a foundation topic. So it's a little tiring, I understand. So I mean, that's a break of 15 minutes. So we'll resume at 11:35. In the meantime, you're welcome to do you reply or ask any question that go around.
Professor, I was wondering in the beginning that, like I understand that there's equal probability in a simple random sample, but I was wondering if there's replacement, if it's independent.
You know, replacement. There's no replacement. Without replacement, then what you join the first is the second, so it's not mutually exclusive.
Yeah, so I was wondering, like, if you had 1,000 people, that's technically not a simple random sample, because if we chose 100 people, like when we choose the first one, then we affect, like,
Yes.
So this is not applying to like a poll or something like.
Maybe there's some way to make sure that it's going to be high.
Oh, so it's okay. That's what I was trying to.
Yeah, that you need some sort of way to figure that out.
Oh, okay. So like when you were talking, because I was also wondering when, like, you know, we have the population 1, 2, and 3. And then, because I was thinking there can only be 3 samples, or I mean, yeah, 3 samples of 2 if it was independent, but there would be 9 if it was.
Yes, yeah, that would be some issue when you apply in practice, how actually you collect a single random sample, but as I said, if your sample size is large, then there's some
Doesn't
that
matter.
doesn't.
Oh, okay, yeah.
Right, that is the same idea, but that being said, that is assumption that we make for most of the paper. And that is usually not an issue there, as long as it's supposed to have a large population, but draw based on say security number.
Okay, that
you have 1 billion people there, right? You only draw 1,000, end up the same number. That's impossible, right?
Okay, yeah, that, because I was, because when you said independent, I was thinking like, you know, when I did survey in school, like, I guess it was population, because like, when I choose 10 people from the class, and I choose, you know, for an Albert, then everybody else.
Like this class, when you draw, but if you like more than 100,000, then probably it's not, usually it doesn't really matter. But of course, mathematically, there is some different way to correct adjustment.
Don't worry.
I mean, that part is the error from that part is so minor compared to all other things.
No, that's definitely makes sense.
Yeah, but I hope I convince you that, but all the undergraduate class now, I think most of them will just assume it's a simple random. How to adjust is say how to do sample, get something very advanced stuff. There's a certain way you try to draw samples so that make sure that you still get the same thing. For a stratified sample, which is then with some slide, so tell me how to make sure that it's happening.
All right, that certainly makes sense. So
But the main goal is like to the data is representative of the population. That is the main goal. A simple random sample is the way to make sure that they happen.
to go about doing it. Okay,
As long as what you draw the first one, second one is more or less independent, then it shouldn't be.
I see your point with like 1,000, you're like 1 million people doesn't matter. You're not gonna get.
Yeah. If you have very small sample, population size very small, then you have the issue there. I mean, there's some way to handle that. Say especially for the medical research, that would be an issue. But for business, usually do use not a big thing.
Oh, well, I appreciate that, Professor. Thank you.
I think it's not a problem. I mean, say for financial data, then that's a problem.
This
That's a
is no
problem
problem.
because the price, so the data you got is time series, because of how the price progress along the time. So each observation you observe is not, right? Today's price partially with the yesterday price, right? So it's not a thing, right? And I mean, we need a much way more advanced than
The
so
sample.
that's why that would be.
But now it's like I understand the difference. So like, in the independent sample, it's with replacement, basic, this is the fundamental way of understanding sampling, but in the real world, especially like, so like, if we have like a lagging indicator, that's definitely,
Yeah, there's some way to solve it.
there's some way to solve it.
But we are not, we're in the class to solve that. That is something advanced class, but there's some way to handle it.
There is.
But in the introductory class, it's always like it.
Okay,
Okay,
that makes sense.
I mean, there's a people who window well classes. Look, handle the time series table and go. Know how to handle that. I mean, handle the time series.
The notebook.
Graduate for salad. And go with time model. Auto-regressive moving average.
I never.
I mean, you don't run the regression and control the error. How the error tests progress. That's something. Don't worry. You mean if you go further, then you this thing will be handled nicely.
Okay, I appreciate that, Professor.
Because if actually that's why you know how to do that. So that's why we know how to do that.
Oh, cause hypergeometric.
If you do sample with that is supposed to
That would, And so the difference being, well, that is the sample, but the probability is the probability of a certain sample being. Okay, that makes
So
sense.
then it's then they use small sample. For central image throughout the finite sample adjustment.
But in theory, I mean, it's very complicated because it's not just success and failure, but if we calculated the,
Oh, that would be some way to handle that.
okay.
That's why we're doing one cost to study all those straight, right? Even the time series would be one semester course or two semester course. How to handle this kind of sampling is already one semester course. Because if you do data for it, then you know how to do data. That is not not something we can cover in the class. But just assume this happens. Don't worry, most of it will be there. Just so some adjustment here and there. So it's not something like change the whole thing. Just like Newton, right? Newton second law. When you have a friction, so don't worry, not going to check the fundamental thing. Just like some adjustment, the formula here and there, everything. So don't worry about it.
I
It's
appreciate
not something
that.
like when you learn something new, everything just fresh start. No.
Thank you.
So don't worry about it.
你呢個真係 highest value function
快啊！
爭過，
你真係好
因為
佢爭晒
呢個你咧
係 Excel 冇得打1個鐘
真係嘅啦，咁你
我個呢個 Excel 佢同其他大書科
嗰個叫咩打？嗰個叫
用數字讀書
就 random 連抽啊，就會抽到你。
抽一咪你三個都有。
你少少賺，俾我打 True False 啊！
咁你如果你有兩個，可能第一個
包得去到
成功次數，抽出係 sample，
睇晒。
成功次數係咩 X 啊？冇成功次數係 X，我睇成功次數係。
即係你講
抽出係 sample size，我係 N
1到1、2、3。
我覺得佢難用係強大嘅中國語言係呢個可能性。呢個出嘅係咩？
睇你抽到咩機，咁咪當講三文講，佢數幾多數？
咁樣就係因為佢得抽一次，跟住係一組數，下邊就係抽兩個數，咁抽兩個數就9個可能性，跟住9個可能性再計翻，即係
我知人，即係嗰個
即係抽下邊個 better research。
我哋呢啲去講係
因為我想
直接 test 晒自己，係咯，
我呢個
你
打出
你計翻個
我再睇出
好傾講上，
research 點解佢要？
佢想用
係啊，成日
我想用特別嘅方法去計。
你唔見佢條色全部都係 C 嚟嘅咩？
佢用 C 嚟㗎，你諗下先，
佢條色就係 C 啊！
我咁你咪七，我唔想計啊！
好簡單要食，我啱係仲麻煩。
係咯，唔係仲難理解啲喎。
呢個呢個詞呢個舒服，即係你嘅詞
出嚟嘅。
我就喺度，我諗應該搞你做幾錢呢個 A 啦，你答嘅問題又唔係你整嘅問題啊，
即係都係 C 啊嗰啲嘢，C 同 C 嗰啲。其實我邊係咪本身我一個係文字嘅讀法，
所以就可以
根本唔需要大
你
嘅名詞去特別去記。呢條色顏色先有發顏色對全部都發過嚟。
然之後下面嗰條咪1減x 等於1 x 等於2同埋 x 等於3，即係以前如果你想要加或者
咁邊度係啦？
我讀即係 success， 佢做得好好。 呢個係得科數，佢冇得俾你。仲簡單。我哋先翻字。我翻嚟覺得呢個方法。
方便在哪兒啊？
即係我打咗個數值。
我中意呢個答案。
佢幫我省略咗一個步驟，即係實呢個有數。
咩步驟啊？
我連試都唔使試啊！係呢個乘呢個對呢個，咪調翻轉除翻。
我嘅方便程度要係一個計數機我撳得到。
你而家要增加件事先嚟。個數機
咁樣到係
先嚟咁撳。我完全覺得 DSE 好麻煩。對唔住，我覺得好麻煩。咁所以你咪就係你要實。
幾想贏？
咁你係叫你做咗幾次嘅賽，然之後試啊？
換咗個班團真係。
你嘅定有啲嘢就係
開 Excel 就已經方便啦，你又要點樣抽嘢？
呢個科目最搞笑嘅，因為佢哋好大。就多幾條 curve 嘅，即係你就畫呢個 M 之後，跟住呢個 R，之後呢個係
啱啊
，M.P 啊，M.T 又係好似係有一個打一個打，好似係啊。點解我抽一個係冇可能？未攞過就標誌，但係佢哋我摸定 free 啊，佢要答問題。我哋 free 嘅 step 鬼衰啊！你要麻煩啲講。
思維特嘅，
我直接
用中學方法要難啲教
收皮，呢個我唔夠啦，唔夠講啦，我唔夠講成但係你用呢個方法咧，幫你搞啲靠自己。
真係自己做
我完全唔知做乜。
你都係。但係你自己會兜咗個圈，困住自己啊嘛，你明唔明啊？
試下。
即係你自己都搞到自己唔明係。
係啊。你講其實我搞完佢考試有次，考試有識我撳嘅，但係算。
又俾我哋俾你用係，
之後唔緊要，但係你個所謂 Excel 都撳得，你個級數。
但係
呢個
管理唔到，
係啊，我都嗰啲死咗，係
香港係需要自你做到得。
佢其實佢嘅佢自己其實唔食啦，輸過。你諗下，你唔係現場俾人抽問啊嘛？
你哋呢一科嘅方面，
即係識得你專業啲。我識專業時做嗰啲，我一齊做。
因素嘅問題，
一個人係T 三十輸三，
你
應該冇乜人食到 T 三。呢個食到啊！
分析數據咯。
其實我諗點解
好 depends 啊，
係啊 ，depends。
好 depends 你揾翻嚟嗰個數據上去。depends 你揾乜嘢？
我點解佢仔？
如果揾啲好雜嘅嘢，可能真係每班就係2班。
I hope you have a good break. Let's see whether we are too fast or too slow. As I said, this is the foundational class for the rest of semester, so it can be a little bit boring and maybe too fast. I'm not so sure. But anyway, if you have a question, please feel free to leave your message in the U reply so that I can try to explain a little bit more detail. Because people in Asia tend to be more reserved. in terms of asking questions. Just by the way, if your questions, feel free to raise your hand. Otherwise, I'm not sure whether I got you or not. Okay, can I just explain more? Page 18. So the main idea is the following. The idea is that the sample mean itself is a distribution, right? Because it depends on sample you got. So the question is, what's the variation of this sample mean, right? Because you have many sample mean, right? Then you want to calculate the variance of all possible sample mean. And turn out to be, this variance can be calculated. I don't want to show the proof, but turn out to be very nicely. It just depends on some inverse proportional sample size. And the variance same as the original distribution, okay? Depending on how spread the original data is. But it's scaled down by the factor of n, it's a sample size. The bigger the sample size, this dispersion of sample mean to get squeezed. And especially when n go to infinity, this go to 0. I hope I answer your question. If not, then please feel free to take there. Yes. So the question is, can I describe the statistics at random? Yes. That suppose you should mean that thing. Okay. Unless you got every single thing that in your population. Like suppose so it depends on the population you concern. Okay. Suppose you only concern about, say, DUHK student statistics, the data. And if you have the data in the university, you get everyone's data that is not random variable, right? Because there's some that's thing you care. Right? Suppose I care about the mean score of midterm exam for this one. I'm doing a midterm exam, but suppose a midterm exam, right? I have everyone's midterm score. I calculate the mean. That's not random variable, right? If I only care about the score in this class, right? But if you want to use data to predict what's going on, then what you observe is a random variable. Does it make sense? Okay. Sleepy. I'm so sleepy. Yeah, I'm very sleepy as well, but that's why I have coffee before I come to class. So hopefully you got some coffee as well. I think there's a coffee shop down the hallway, across the hallway there that you can try. I go to school by bus. Seriously, because I don't think there's a good bus come to, I mean, subway is more often, but bus is not that easy. But I think if you're not from Hong Kong, you don't know the joke, but I think I go to school by bus is the joke that local people make, because this is the first, probably one of the first few sentences to learn in the primary school kindergarten. So that's why they put a job. Do we have answered homework? Yes, I think we do. Then I will ask the PA to release that. There will be solution to that. Yep, that's great. No one mistaken today's days. Yep, it's raining. Okay, it's cloudy and windy. Yeah, that's okay. Yep. So Aaron will talk very soon, but that actually we have already hinted already, right? Because of when n goes to infinity, the variance shrinks, right? And average of the mean is going to be there, so that's why it will be there. It will be exactly there. And no, this is not Aaron. This is central limit theorem. Because the two things. Law of large number said when the sample size get very large, then sample mean actually approach to population mean. Okay, that is. And central limit theorem said the distribution of the sample mean follow a bell curve. Okay, so they're different, but more or less the same, right? Because n go to infinity, the bell curve will collapse anyway. So I mean, it's correlated. I mean, of course, it's not that class. I'm not going to ask you what's LLN, what's CLT, but they are very important concept. Okay. Mean variance, yeah. LMO. Yes, statistics too many. Yeah, too many is the key point because when we have many sample that we have nice property there. Okay, there's too many is the key point. I mean, that's right. And yeah, we have some okay. Oh yeah, it's getting cold, so it's getting, especially by for those who are new to Hong Kong, then we're starting to get cooler by the end of October. And also the temperature is not very low here. But the fact that we're close to the sea, the humidity, and also the way we build the building, is cooler than in the US. I can say. I was studying US, so I can compare to that. I can say it, and also I compare to the. When I go to Europe, it's also actually here is more cooler, unfortunately, the same temperature. Tonight you have accounting. Was it good luck? And because of your score is a random sample, it's a random variable, right? Depends on many things. So hopefully you got a good luck. And that's the reason why in many classes there are many quizzes, right? Because you want to average out, right? But in our class we only have one, but it's unbiased, right? So even one sample is okay. But we have many questions, so that's okay, right? So it's okay. There's many questions reflect what we know about you. So let's check out, because I think many people are very tired. Oh, hopefully this make you less tired. Let's see what we have. No. Oh, it's not here. I always feel not easy to handle this. Okay. Let's see this and see if we have something.
Tiramisu soft serve. Hello, 新嘅企，我係阿 Greg，呢個係多葱 Bakehouse Number 6 ，follow me。我哋有三份嘢，有奶茶 Honey Toast， 有蝦子卷，跟住有 Tiramisu soft serve。Honey Toast 係好似茶餐廳嗰度細多士奶茶，我中意食呢個，跟住有 Honey Glaze。Caramel around 我哋 sourdough croissant 度啊嘛，有奶茶忌廉，呢個咩度？就好蝦子飯咧，嗰度圈咧，有好多umami嘢，有 parmesan cheese， 有葱，有 garlic powder， 咁 together 咧好正啊！我哋 cold brew coffee tiramisu， so mascarpone soft serve。Cocoa powder and caramelized almond strudel.
Okay. So I hope you feel sleepy, then have some food video make you happier. I think the research have shown that when even you don't eat, by looking at the food video will make you happy. Okay, that is a scientific discovery. So I hope this class can be very boring, but looking at some food video make you feel happier. Let's so I think there's some time to quit you. I don't know. I mean that hopefully you don't, but if you have to, then good luck for the rest of your life. Your assignment is not given full marks. As we said, you get 80% of that, right? So if you make some mistake, then we take away some of the marks. But I can almost safely say that your grade usually not dependent on that. I mean, I think no one would actually have grade difference because you don't get perfect score from your assignment. Okay? If you don't do assignments, other thing, but if you get 80% by just trying, right? Then usually there's no difference between you get X 9 or 10 score. I mean, that would but if you really insist on getting perfect score, then probably you should ask TA to ask why you don't get perfect score. In the case that you are very care about the 1 minor point there. Okay. So that is law of large number. I think we have said already, but I just try to make it formal. Okay. The main idea is that, right, law of large number said the following. Is when the sample size is super large, okay, we would eventually, the sample mean will eventually same as the population mean. Okay. Note that the n can be super large, right? Have to be so large, which is always not possible, right? But right. But at least in theory, that is possible to get the ground truth, right? Which means that when we do a lot of sample, the sample mean variation strength, right? So when you go to infinity, that go to 0, and we know that on average it's mu, so eventually get there. That's a proof, of course. The real proof actually is much more complicated, right? And we do have a formal definition. Okay. There's a formal idea there. I mean, of course, because limit is not something well defined by itself, because this is probability limit. So how do we define? I mean, there's a definition, and I mean, maybe I should make it gray because I'm not going to ask you anyway. But it's a formal definition. It's saying that, okay, for any epsilon bigger than 0, I can always make this within epsilon distance from the true mu, that is going to be 1 as n goes to infinity. So I take a limit outside because that is the statement there. Okay. But I don't want to go to the proof, but the proof actually relies this real statement. Okay. But roughly speaking, just like the idea is like the bigger the sample size, we can go as close as the true mean as close as we want if we get n bigger. But I'm not going to explain this part. But this is the real statement if you really want the formal statement. I'm not going to talk about that. So n go to infinity is the x bar n. This is the n. This is the part that go to infinity. There's a proof. I'm not going to talk about proof. Okay. Now, here what we want to say is that law of large number is very useful by itself. The statement we know, but that part is not sufficient because we actually want to know how it looks like when you get to infinity, right? You say eventually it's there, but how the shape not clear. So turn out to be very nicely the shape is bell. You as close to bell as possible. Okay. So that it means is as you get n get bigger and bigger, the distribution, the shape looks like the bell, and that is the underlying reason that bell is the fundamental thing when you talk about data. No matter what you do, bell is the thing, right? As long as the data is simple random sample, bell is the key to go, right? But if not the case, then we have other techniques that is not what we cover in the elementary level. So there's something called bootstrapping, multi-color simulation. All these things actually go there. But in our world, we focus on simple random sample. The bell is the thing that we will get, okay, because of central limit theorem. So here's to convince you that this looks like a bell. Remember the question, we have sample size. One is like 1/3 for each one, like uniform distribution. But after this, when you're 2, then it looks like it's a triangle, right? And 3 is getting like a bell, right? And 4 is even more bell, right? The 1 actually get, and 3 get smaller, right? It will become this like this, right? If you try to draw it, maybe this, I don't have a table, but maybe I should draw one, right? Because that would be something like, right? If you have the data is like 1, 2, 3, right? Right. If you draw a table, this is P, right? That's what we get, right? And this is the data, original data we have, right? This is 1/3. And what we have table we have seen is like this, right? X1 bar is like still 1/3, 1/3, 1/3, right? 1, right? And if you have X of 2, it becomes something like this. Right? And then if you have 3, then it looks like more like this, right? And at the end, you will see the more you do, you'll become a bell. Okay. And at the end, it will squeeze out the bell shape. That is what it looks like. And this actually generalized, right? And that is what we call the formal statement for this is turned out to be like this. Okay? When n get very large, the X bar will be looks like a bell curve. Okay. So you look at this has no assumption on what underlying F looks like. Okay. The population can be very crazy, can be like uniform 1, 2, 3, right? Can be anything. We don't have know the underlying looks like, but the sample mean be normal, right? The population can be Poisson, can be exponential, can be hypergeometric, can be anything. Okay. But the sample mean will be bell. So that is an amazing part, right? Regardless of what you do, it's bell. All right. So that's why I said, well, no matter the gene distribution, right? At the end, it's a bell, right? You don't really care about how IQ is being generated, the height, the weight, whatever, how it looks like, as long as this is IQ is the average of many effects together, and it's bell. So that's amazing part. That's why we call normal. And the bell is a normal because everything we observe is a combination of many small parts. Right? So that's why it's a bell. And if you express this in formal way, we'll call this item we've seen very often follow a standard normal. Okay, minus this over this guy is called standard normal. Okay, this is the exact formula for central limit theorem. I mean, this is approximation, but this is the one that we care. Subtract the true mean over the true standard deviation, the standard error, right? That is the thing. Okay. And one thing you want to ask, okay, we never have go to infinity. Okay. The question is central limit theorem a good approximation? Turn out to be, we don't actually read very large n. Turn out to be n is more than 30 something. Central limit theorem will be a good approximation. Of course, the larger the better, but when it's about 30 to 40, then usually there's no big deal. Okay. Of course, there'll be some concern if less than 30, right? Less than 30, you need something much more. But I guess for business application, less than 30 is not, it will not be there. I mean, of course, for the medical study, way often less than 30 or 40 may be not unsurprising, but for business application, it will be 100 or thousands, right? So it shouldn't be a big thing. That's what we have is like bell curve apply. Now, let us try to see this question, and then you will probably appreciate why we need that soon. Okay. So suppose a population with mean 5, variance 64. Do note that I didn't say how the shape looks like. I just need to know the mean is 5, variance 64. Okay. And I just try to get a random sample with size 100 to that. Okay. And the question is, okay, suppose this is the case, how likely that I get a sample mean no more than 4, right? So probably X bar is less than 4. Okay. And because of this sample size is more than 30 something, so central limit theorem applies. This thing actually would follow the same mean, but variance will be a fraction of the sample size is over 100, right? So 64 over 100. Okay. In that case, then we can actually do the calculation, right? Is this X bar less than 4, right? And then we can do the same technique, right? We do the standard normal minus the mean over the SD, okay? And we do all the bunch of calculation, then you can end up with 1%. Is that okay? So it's a bell curve, right? X bar is a bell curve. Okay, we know that. Okay, so that's the question. Just in case you are not happy, let me draw a graph here. So central limit theorem tells us the following. X bar of 100. Okay. This represent n is 100. Okay. I use this notation. So we'll be having the mean of 5. Okay. And the variance of this guy, okay, will be 64 over 100. Okay. And the question is asking how likely you get 4. No more than 4, so mean this area. Okay. So if you want Excel, then will be norm this 4, mean is 5. I think you put SD, right? Then it's like 8 over 10, right? Because root 100 is 10, right? And then true. Okay, so that would be the. This is the case. I think this is a. Let me try. And that should be the case. Four, 5, 8 over 10, 2. So that is the way that I calculate that one. Of course, to look at a table. I told you how to look at a table because in exam that's what you should do, right? So that would be how you calculate that guy. Okay. And at this moment, you will wonder why you're going to calculate this thing. Very soon we'll know in the next topic. Okay. We'll just tell you that that is another bell curve. So basically what we do today is like, okay, there's a bell, and then you can do all the probability statement over that. And how we use it will be the thing that we do in the next 2 chapters. We do in estimation, hypothesis testing, we need this understanding of how the sample mean looks like behave. Okay. And that is how why we do that. Okay. I hope. I mean, now probably still like why we're doing this. It's unclear, but it'll be clear when we do the next 2 topics. We need this information. They follow a bell curve to do all the things that we do. So as I said, this class is, and the next class will be a little bit boring because we don't show you how why is useful. Okay, but I hope this after The next class, then we're getting more interesting. But because this class is we're not applying anything. We just tell you, okay, what the sample mean looks like, okay, and what property of that, and then that's it. I mean that we don't do application, but soon we will do application. Okay. So that's what we have. Okay. Now I want to draw your attention on the binary case. Okay. The binary case is either 0 or 1, just like whether they support Trump or non-Trump, right? Or they're man or not man. Okay. I want to say woman, but may not be appropriate, but there's something if non-binary, then it's something man and not man, right? Or are they pass exam or they don't? Okay, it's binary. Okay. And the proportion, right, is how many people in the population is 1, right? So say I want to know how many people in say CHK are female, right? Or how many of them actually have a account in Netflix or account in Disney Plus, okay, so on and so forth, right? That is the proportion, okay? And you can easily see that when you have 0 and 1, the sample means actual proportion, right? Add up all the 1 and the 0 over how many of them is percentage, the fraction of the people actually there. So that's why the sample mean is actually the this data is the proportion or called pi. And the variance turned out to be, perhaps not surprisingly, it's just pi times 1 pi. And that is the Benoni distribution. So Benoni actually is p times minus p, right? I'm not going to prove it, but you can actually check the variance is actually pi times minus pi. Just if you don't believe me, then take look at the proof in the slide, but I'm not going to cover it. But let's take it the face value if you don't want to. Okay. So now consider a case where you just pick up a individual from the population, okay, and that is a Benoni, right? Because it's just like 0 or 1, right? And the success is just pi, right? Because how likely is it? Just how many of them, the fraction of them, right? Pi. And the variance turns out to be exactly the same, which is not surprising because it's what's supposed to be, right? You just draw 1. The variance same as the original one. It's called simple random sample, right? We have that definition there, right? So, this is the proof. I'm not going to do any proof, but if you want, you can check it out. It's more tedious proof. Okay. But what is new here? Okay. But probably may not be new to you. I mean, it's the sample mean, which we have already. It's called the sample proportion, right? Because you collect the data, check how many are female, how many are male, right? The ratio of the female over total population, right, will be this sample mean, which is sample proportion. Okay, we use the notation P because this is what textbook is using. It's called P. So what's the goal? What we want to do is we want to know the pi, right? We want to know, just like the election, how many people are going to vote for Trump or how many people are going to vote for Harris, right? The proportion, right? The sum of the P is trying to guess what is the big pi, right? Or I look at how many people like statistics in this class, right? And I ask some of you and then try to guess what's going on in the big picture. So that is the goal, right? And it's often used, right? Is we want to care how people like your product, right? In business. Okay. And because sample proportion is just a sample mean, right? So everything we discussed so far applies. The central limit theorem, law of large number, everything apply, right? So the sample proportion, the expectation is same as the population proportion. Nothing new there. The same. Just rewrite the notation, right? But one thing that's different. That's why we need to say special case is when we know the sample mean, okay, the sample variance is related, right? Because you do remind yourself that, okay, mu and sigma squared in general, they're related, right? But for binary data, mean and variance are related, right? Mean times the variance is just mean times 1 is mean, right? So that means that the standard error or the variance of the sample proportion will follow this formula, okay? And this is important because later you will see this give us a very convenient way, right? Because when you have binary data, when you know the mean, you know the variance. You know the variance of the mean, okay? And then they have to go hand in hand. So when I guess the mean, the variance is immediate, okay? But there's nothing new here, but just the formula, right? We don't have separate formula for variance. One is sample mean, variance there, okay? So that is something that we will use that. I mean, this is just stay there in your slide. We'll use it later, okay? And this is the part that you have to remember. I mean, this is the main result, okay? The main result today we have is this result is this guy and this guy. If you forget everything, there's a many things. The main thing you want to remember is this. The sample mean, follow the bell shape, okay? This one. And the next one is the special case is if binary data, okay? The variance is pi times 1 minus pi over n, okay? And before this is sigma square, but now replace by pi times 1 minus pi, okay? And that later you will see this is a very convenient thing, okay? But of course, again, the question is rule of thumb, right? Before we said when n is more than 35, that it works. What about this guy? Okay, and turn out to be we need the n pi or m times 1 pi at least 5. Okay, so if pi is very small, then you have to get a big n to be useful, right? Otherwise, that can be an issue, right? Well, what happened to that screen? I think it's okay. Okay, that's fine. Coming back. Okay. So there are 5 minutes, but I don't want to go further. But I just give a very quick note on what we're going to do next week. Okay. The question is, it's very nice that we know that this is normal, right? But the main problem is we have no idea about sigma, right? We know that x is around the true thing mu followed by bell curve, right? But the problem is we don't have sigma in general. Okay, we don't have idea. Okay? There's no way you can estimate that. Okay, of course, there's some way to do it. You can have upper bound. Say look at the data, the range divided by 4 will be an estimate. But usually, I mean that would be one way to do it. But I'm not going to oppose that step. But how do we handle this problem? Okay, turn out to be this related to the t distribution we don't talk about, and turn out later we are not. The end of the day we'll talk about next week is the following. Okay, very similar to what we have. Is if we replace the population variance by the sample variance, it will follow what we call student t. Okay, and do you look at this we need an extra assumption compared to the central limit theorem. Central limit theorem don't need to assume anything. There's no assumption. As long as random sample is whole. But this student T requires to make the assumption that the underlying thing is a bell. Okay, you ask if not bell, what happened? Okay, that is another issue. But assuming that the data itself is a bell. Okay, you assume that the overall the IQ in the population is a bell, which is okay. I think it's okay. And we collect data from that, then everything follow the T. Right, so that's ID. But that is not an issue because when you think how the IQ is being determined is many factors add together. The second rep apply. So that's why the population is still a bell. So it's not an issue. We apply central minimum twice, right? Because the population actually generated from the nature follow a bell curve thanks to central minimum theorem. And then if we believe that's the case, this guy, okay, we can apply the central limit theorem to show you that actually the sample mean follow almost a bell curve, right? Remember T is a bell curve, but a deformed one, more smashed at the top one. Okay, that's something we talk about in the next class. So don't worry, we will see you next Monday on this. Okay, enjoy, and then hope that you do the assignment too. Okay, when you have time, and good luck for those who take the exam tonight. I see you next week. Enjoy the weekend.